Okay, good morning everybody and welcome to Analog Electronic Circuits. This is lecture 2. In the last class we were looking at a simple nonlinear network and we concluded that fundamentally finding the branch currents and the branch voltages and thereby the node voltages in a network which is nonlinear is a difficult job, right, because you get a system of equations which is nonlinear in the network unknowns, namely the branch voltages and the branch currents, and these are also coupled. To solve them, you would most often have to resort to numerical techniques unless you are happen to be particularly lucky. Now, however, we said that once you find the branch voltages and branch currents with a given excitation, right. If you change the excitation by a small amount, then the changes in the branch currents and the changes in the branch voltages can be related to each other with a linear equation, as we saw in the simple minded diode example yesterday, right. And this notion of small signal is was related both to the nature of the nonlinearity, right, the function, as well as the quiescent operating point. Okay. Now, so we saw that for a simple diode network, and what we concluded was that if this was capital V1 or Vi and this was our network, this was some R and this was Vo, then and if this was I, then when we changed the excitation to Vi plus small vi, then the resulting output voltage would be Vo plus small vo, and likewise the current would be I plus small I. And by writing out Kirchhoff's voltage law around the loop and subtracting the two voltages and so on, we got a network relating only the incremental quantities, and assuming the signal Vi, small vi is indeed a small signal, we found a linear network relating the change in the branch currents and branch voltages to the change in the excitation. Okay. And this is, since this is, represents only incremental quantities, this is called the incremental network. Also called the small signal network. And from the small signal network being linear is very easy to evaluate, right, and in this case the small Vo is by inspection seen to be simply capital R over capital R plus Vt over I times Vi. Is this clear? And so what have we done? If you stare at this picture, we have seen that we have replaced every nonlinear element by its incremental equivalent, right. The two terminal diode, though nonlinear, around the operating point, the change in the current through the diode can be related to the change in the voltage across the diode by a linear relationship, and therefore as far as changes are concerned, di by dV of the diode is a conductance of value I over Vt. The capital I is related to the quiescent operating point, and the particular nature of this small signal relationship comes about because of the exponential nature of the diode, right. If the diode had some other characteristic, then this formula for small signal resistance as a function of operating point would be different. Okay. Now, this is for a simple network, and remember what we did. We wrote the equations for the original network. We also wrote the equations for the KVL equation for the network where the excitation has changed, and then how did we get the incremental network? We wrote these equations, we wrote that equation, and then we subtracted the two equations, right? Then from that, I mean, after making the small signal approximation, we got an equation which was linear. From that we got the network again, the small signal network, right? It's kind of eating like this, right? You have a network, you write the equations, then you have a slightly different network, you write the equations again, you subtract the equations, you get another equation. From the equation you go back to the network. It doesn't seem to make sense to write equations, go from network to equations back to network. It seems reasonable that there must be a way of going directly from, I mean, given the two networks, we should be able to draw the incremental network right away without having the need to write the KCL, KVL equations, for each network, subtract and all that, right? Rather than subtract sets of equations, it's likely that we will be able to subtract the networks itself. We'll see what that means going forward. But so let's take a generic example, and so all these elements could either be linear or non-linear. I am just taking some picture like this. Okay. So, this is let us say capital V1 or V in, and let us number these nodes 1, 2, 3, all right, and let us number at least some branch. Let us call this say I1, and I2, capital I3, I4, I5, okay, and I6. Okay, so we have numbered the branches. So the voltages across the branches are going to be V1, V2, etc. Okay, I am not labeling all the branches. The idea is that if a current I5 is flowing through a branch, then the voltage across that branch is capital V5. Okay, all right. With this background in mind, let us now and these elements could be linear or non-linear. Now, what am I doing? Well, I am going to basically increase the excitation by a small amount. Consequently, what comment can we make about all the branch currents? They will also change by some amount. So, this current which was I2 will now become plus small I2, this is small I4, this is small I6, this is small I5. Does it make sense? Okay. Now, quick question. If I add, and I mean likewise the node voltages, V1, V2, V3 will also change by by small amounts. Now, quick question, if I add to this node a current which is 0, what comment can we make about the branch currents and the branch voltages? Now, there is no change, correct? All right. So, now if I pull current out in the opposite direction, what comment current out which is 0 in the opposite direction, what comment can you make? No change, very good. Okay. Now, I would like to draw your attention to an observation. What comment can we make about I1 plus I3 plus I2? That must be 0 because of they must satisfy Kirchhoff's current law. Okay. Now, watch carefully as I do this. I am going to add a current source like this, in the opposite direction. I am going to add a current source like this in the opposite direction, and likewise I am going to add a current source like this in the opposite direction, and I am going to do that for all the branches. Okay. Now, what comment can you make about the node voltages and branch currents? What comment can you make about the current, I mean about this node voltage? Why? Okay, well, there must be only three answers, either the voltage will reduce, or the voltage will increase, or the voltage will remain the same. Remain the same, why? Why do you say the voltage will increase? No, how many, what is the current being pushed into node 1, net current being pushed into node 1? No, what is the extra current that I have pushed into node 1? Yeah. So, I have added 3, what is the net current that therefore going into node 1? And what is I1 plus I2 plus I3? Is 0. So, there must be no change, simply because at every node I am injecting a 0 current, right. And how did I get that 0 current? Because I am looking at I mean how are these I1 and I2 and I3 currents derived? Are they arbitrary? Are they arbitrary or what? They are the currents in the original network, which all satisfy Kirchhoff's current. Does it make sense, folks? Okay. All right. Now, by the same token, what I am going to do is I am going to introduce in each branch a voltage which is in the opposite direction as the original. Okay. Begin. This is minus, this is sorry, V4 and capital V. All right. So, the voltage here was V1 plus small v1, this was V2 plus small v2 and so on. So, what comment can you make about the net voltage added in the loop? By the way, what is looking at the original network, what comment can we make about V in minus V1 minus V4? It is 0 because that forms a KVL loop. Okay. So, what is the net voltage I have added in this KVL loop, in this loop? The net voltage I have added is 0 and therefore, there must be no change in the loop currents, correct. Similarly, if we do that for every branch, so basically what we are doing is replacing every branch therefore with, so if there was an original branch like this with some ik capital Vk plus small ik plus small vk, what have we done? In parallel with every branch we have added a current what? We have added a current capital Ik going in the opposite direction, all right, and in series with every branch we have added a voltage source there. What is the value of the voltage source? Capital Vk in the opposite direction, correct. And we just discovered that if we replace every branch with this contraption, then KCL and KVL will be satisfied at every node. Does it make sense? Right? Okay. I hope you are able to see the construction. What are we? I mean, essentially, what are we doing? Basically, we are writing out KCL, KVL equations, subtracting the two. Rather than writing the equations, subtract the two, we can do this at the network level. Correct? Okay. So, now if you do this, what comment can you make? You can think of this as a branch. What is the voltage across this branch? Small Vk and what is the current through the branch? Small. All right. Now, does this depend on small signal operation or this is true for arbitrary changes in excitation? Arbitrary, why? Pardon? We have not made any approximation whatsoever. We have just used KCL and KVL and then just made some connections and it seems like. So, this is valid for all values of excitation. Does it make sense? Okay. Now, when we make a small signal approximation, what are we going to do? If the excitation was a small signal one, what comment can we make now? Can we make a further simplification? Yes, what is that simplification?
We can find the relation between
So, if the signal is a small signal, then an additional thing that you can do is to relate the change in the voltage across this branch to the change in current through this branch by a linear equation. Does it make sense? Okay. And how do we do this? Well, if the capital Vk is some function of the capital Ik, for instance, then the capital Vk plus small vk is a function of capital Ik plus small ik, and therefore, this basically means that small vk is approximately equal to dou f or df by di. There is only one variable here. So, df by di evaluated at I equal to ik times small ik plus higher order terms, which we already saw, right, basically will define what it means for the signal to be small signal. But in general, if we assume that those higher order Taylor series terms are negligible compared to the first order term, then this is the, what are the dimensions of this character? This has got dimensions of resistance, and therefore, this can be replaced by a resistor of value df by di evaluated at I equal to ik. Does it make sense? We did this in the special case of a diode yesterday, right, but this is now true for, as perhaps not surprisingly, it is true for an arbitrary nonlinear network where you have all sorts of nonlinear components. Finding the operating point is going to be a difficult affair and has to be done numerically, but once you find the operating point, if you change the excitation by a small amount, the changes in the branch currents and the changes in the branch voltages can be related to the change in the excitation by a linear network. Okay. Now, the linear network may take time to evaluate, but if the network is big, we know that the linear network will be big, but we know how to evaluate it. It may take time, but we can do it, right. Whereas, with the original operating point calculation, it may simply not be able to do so analytically. You have to go for numerical techniques. Does this make sense? Okay. So, so the bottom line is that now what is the advantage of basically this whole exercise here? Why have we done this exercise? Pardon? From the main network, of course, you can derive the incremental network, but let me kind of step back a little bit and motivate why we are doing this small signal analysis in the first place. We, as I already told you, we spent a lot of time learning about linear networks and ways to analyze them, correct? And then, but now we find that all our networks are nonlinear. That basically means all that studying is apparently a complete waste, right? Okay. So, there are two ways to go about it. One is to say, now our previous teachers have played a cruel joke, right? Because they have taught us what they know, but unfortunately it looks like none of it is applicable in practice because nothing in the world is linear, correct? Okay. Then the other approach is to say, well, yeah, maybe that is so, but let us try to make the best of it, correct? So, in general, analyzing a nonlinear network is impossible with the tools we have, but let us try and figure out if we can at least come up with a scenario where the tools we have learnt will be useful, and that is we say now that okay, well, let us give up on the fact that finding the operating point analytically we give up on it, right, we go to a computer. However, having found the operating point, we are able to relate changes through a linear network. That means as far as incremental signals are concerned, we can go back to using all our linear analysis tools, right, Fourier transforms, Laplace transforms, except with the small caveat that they only apply for small signals, right. Okay. So, this is like let us say you have an English exam and an essay will come, okay, so all night you open a guide and then mug up essay on cow, okay. So, next day you go to the exam and then suddenly it says the essays, or you read the essay on an aeroplane. So, what do? One thing is to say, well, I do not know anything, and then that is the honest thing to do, correct. But if you are, well, you have at least studied all this, you might as well use it. So, what do? You say in the essay you say, well, there was a plane, I got onto the plane and then the plane took off and then I looked out of the window and there was a meadow and there was a cow, right, and then I read the essay on the cow, right. So, this is like that. Well, you kind of you either say we pack up and leave, right, or we make the best of. Basically, if you think about your undergraduate courses, right, at least half your courses are all dedicated to, I mean, whether it is DSP or whether signals and systems or whether it is linear circuits or whether it is circuit theory, it is all, whether you know it or not, you have spent all your time learning about tips and tricks for analyzing systems that are linear, right, and you do not want all that to go waste. That is the bottom. Is this clear?